Hello, I'm Rebecca Barnes. Welcome to the Science ESA vodcast. In this episode, we will investigate the infrared universe, explore discoveries made by groundbreaking infrared space missions, and take a look at Herschel, ESA's pioneering infrared space telescope. Most of the information about the physical nature of the universe comes to us in the form of electromagnetic radiation, which celestial objects emit at various wavelengths. One way to analyse this radiation is to study the spectrum. Astronomers use a spectrometer to spread the combined radiation received from a celestial object out into specific wavelengths or specific photon energies.
Atoms and molecules can emit and absorb light, leaving a signature in the spectrum in the form of a characteristic pattern of lines. If a cooler gas lies in between us and a hotter source of radiation, the atoms and molecules will absorb certain photons. This produces an absorption spectrum, where gaps appear at specific wavelengths depending on which atoms and molecules are present in the gas. An emission spectrum occurs when atoms and molecules in a hot gas emit a photon with a specific energy or wavelength. The bright lines are again unique signatures of each atom and molecule.
Another way to present a spectrum is to plot the intensity of radiation as a function of wavelength. Signature absorption and emission lines of atoms and molecules will also appear on the plot. The life story of an object can be read from its spectrum. In addition to learning about the composition of an object, astronomers can study its spectrum to find out its temperature, density, and motion. If we go beyond the red part of the visible spectrum, we enter the realm of the infrared. Often, infrared is described as heat that is radiated from an object. But what is important to realise is that what we would consider to be cold is also an emitter of infrared radiation. Celestial objects that emit in the infrared have a temperature between room or body temperature and a few degrees above absolute zero, and therefore a wavelength that is longer than visible radiation. Observing the universe in the infrared allows astronomers to explore the cool universe. Studying atoms and molecules in a region of space provides vital information to build understanding of how planets, stars, and galaxies are formed. Emission and absorption lines for virtually all molecules lie throughout the infrared portion of the spectrum. This means that infrared spectroscopy is an extremely important way to detect these chemicals in the cosmos.
The infrared portion of the electromagnetic spectrum can be divided into three regions: near, mid, and far infrared. As a celestial object cools, it will emit most of its radiation at progressively longer wavelengths, and therefore further into the infrared. Near infrared refers to wavelengths that are just longer than those in the visible spectrum. In this region, cooler red stars become more prominent, and interstellar dust becomes transparent. These infrared waves can glide through thick regions of dust that often envelop many celestial objects, such as infant stars. In the mid-infrared, the cool interstellar dust itself starts to shine. Astronomers can also study emission from disks of material that surround newly forming stars, which one day may develop into new planetary systems. Many objects in our solar system also emit radiation in these wavelengths. The very long wavelengths of the far infrared are emitted by extremely cold matter. In this portion of the spectrum, astronomers can detect the cold radiation from protostars and peer into the centers of galaxies, including the Milky Way.
Observing the infrared universe from Earth is extremely difficult. The light at almost all infrared wavelengths is absorbed by molecules in the atmosphere. And there is another big problem. The atmosphere emits infrared radiation too, drowning out that of the target celestial object. The the clearest view of the infrared universe can be achieved from space. In 1983, the first infrared space telescope was launched. This 10-month mission was a resounding success. The Infrared Astronomical Satellite, or IRAS as it was called, completed the first infrared survey of the entire sky. IRAS discovered hundreds of thousands of new infrared sources and 6 new comets, as well as finding warm but largely invisible dust coming from nearly every direction of the sky. IRAS also presented astronomers with the first ever images of the centre of the Milky Way, a view that is blocked in visible light by a dense fog of gas and dust. Before IRAS was even launched, ESA was planning its successor, the Infrared Space Observatory, or ISO. ISO was the world's first general-purpose infrared space observatory and was a truly outstanding accomplishment. With the wealth of data collected by ISO, astronomers continued to make new discoveries long after the satellite ceased to operate. Let's take a look at a few of them.